The ionization energy. So let's look at the definition of ionization energy. By the way, this definition is very important because it has been repeatedly asked in the past year papers. Okay, ionization energy by definition is the energy needed to remove 1 mole of electrons, the valence electrons, from 1 mole of gaseous atoms to form 1 mole of gaseous 1 plus ions, which are univalent positively charged ions. The 1 plus ions are also known as univalent positively charged ions. Okay, so now let's take an example of a gaseous atom A. Assume this to be some element which is in gaseous state. If we provide it with enough energy, one of its valence electrons will gain that energy. If we provide enough energy to the valence electrons, it will absorb the energy and will get excited to a higher energy level. If this energy is high enough so as for the electron to overcome the electrostatic forces of attraction of the nucleus, the electron will escape the atom and will leave it, and hence it will appear in the equation on the product side. The ion that is formed will be univalent and positively charged. Univalent because one electron has been lost, so a charge of -1 has been lost, and it will be positively charged because a negatively charged ion is lost. So as a result, the number of protons has become greater than the number of electrons in this atom. So when the protons have become greater, so the positive charges have increased because protons are positively charged, and hence univalent positively charged ions are formed. Okay, so in this equation, the enthalpy change of this equation is actually the ionization energy. It's more specifically known as the first ionization energy because in this equation 1 plus ions are formed. If we take this 1 plus ion and give it further energy and remove a second valence electron from this positively charged ion, we'll get a divalent positively charged ion and an electron again. Now, this time the enthalpy change of this reaction is the second ionization energy because this time the ion which is formed has a charge of +2. If we give this +2 ion further energy, another electron, another valence electron will gain it and will be removed first, and the product ion which is formed will have a charge of +3. The enthalpy change of this reaction will be known as the third ionization energy. These ionization energies have a collective term, and this so long as the electrons are removed, we can name the each enthalpy with a specific number, like the fourth ionization energy, the fifth ionization energy, and so on. These ionization energies are known as successive ionization energies. Okay, so now let's move forward to the factors affecting ionization energy. Okay, so now we've learned over here that ionization energy is basically the energy that is required for the valence electron to overcome the internuclear forces, basically not the internuclear, actually the electrostatic forces of attraction experienced due to the nucleus, the positively charged nucleus of the atom. So the energy required to overcome the electrostatic forces of attraction and become free is the ionization energy. Now let's see what factors affect this ionization energy. Okay, so the first factor that affects ionization energy is atomic or ionic radius. Atomic radius when we are talking about the first ionization energy, ionic radius when we are talking about the successive ionization energies, because in that case the electron is being removed from an ion. Okay, so as the radius increases, ionization energy decreases. This is the statement. We'll look forward to its explanation down here, but let's go over the other factors as well. The shielding effect, increase in shielding effect decreases ionization energy. Again, we'll look at the explanation down. And the nuclear charge or the charge density. The charge, basically the nuclear charge density we're talking about. as the nuclear charge density increases, or as the nuclear charge or the charge density increases, the ionization energy increases. Okay, let's go to the explanation now. We've studied that as the atomic radius increases, the ionization energy decreases. Let's see. Okay, as we know that the radius is the distance between the nucleus of the atom and the outermost electron. The radius is the distance between the outermost electron and the nucleus. As this distance increases, the nuclear force of attraction experienced by the outermost electron decreases. Hence, the electron is less tightly attracted to the nucleus, due to which lesser energy is needed to remove the outer electron, and hence the ionization energy decreases. So as we increase the radius, the distance between the positive and the negative charges, the positively charged nucleus and the negatively charged electron, it actually increases. So when the distance increases, the nuclear attraction, the force of attraction between the oppositely charged ions, it decreases. And when the force of attraction decreases, lesser energy will be needed to remove this electron, and the energy needed to remove the electron is actually the ionization energy, which also decreases. Now let's move forward to the second factor affecting ionization energy, shielding effect. Okay, let's see what is shielding. Shielding is basically due to the inertial electrons. It is the repulsive force experienced by the outer electron, the outermost electron, which I've drawn in blue, due to the inertial electrons, as they have like charges. The outer electron and the inner electron, they are both negatively charged, and we know that like charges, they always repel, unlike charges attract. So this repulsive force, which is the indicated by Fr, due to the inertial electrons, it actually decreases the net nuclear attraction experienced by the electron, the outermost electron. So the repulsive forces decreases the nuclear attraction experienced by the outer electron, and hence decreases the energy needed to remove, hence decreases the energy needed to overcome the nuclear attraction. Okay, so if I increase the number of shells over here, the number of electrons which provide the shielding effect, they will increase. So the repulsive force will increase. The nuclear attraction experienced by this blue electron over here, it will decrease. As the nuclear attraction decreases, lesser energy will be needed to remove this electron, the blue electron, and hence ionization energy will decrease. Now let's move towards the third factor, and a very important factor. A lot of questions have been asked in the past year papers. Okay, nuclear charge or charge density. Basically, a lot of questions have been asked from this topic in general, in the MCQs or in the theory part, but they have been asked a lot. They usually ask us to explain the factors that affect ionization energy, and these are basically the main factors that affect ionization energy. Well, I've explained it in quite a lot of detail, but you don't need to explain it in this much detail. You just need to know the key points, which I'm going to discuss in the end. Okay, nuclear charge or charge density. Now, as we know that the nucleus is positively charged, and it's positively charged due to the protons inside the nucleus. If we increase the number of protons inside the nucleus, the nuclear charge, which is this positive charge, it will also increase. If the nuclear charge increases, this attractive force experienced by the outermost electron, it will also increase, and as the attractive force increases, more energy will be needed to overcome the attractive force and remove this outermost electron, and hence the ionization energy will increase. So increase in nuclear charge increases the ionization energy. Now, but the increase in nuclear charge does not always mean that the ionization energy will increase, because when the atomic radius and the nuclear charge both increase, such as going down a group, then the ionization energy depends on what factor increases at a faster rate. So in that case, charge density is used to charge density is used to explain the change in ionization energy. Okay, so basically up here we were considering the effect of the nuclear charge alone on the ionization energy. If we increase the nuclear charge, the nuclear force increases and the ionization energy increases. Now, but what if the nuclear charge is increasing, but the atomic radius is also increasing? We've studied it earlier up here that increase in radius decreases ionization energy, but increase in nuclear charge, it actually increases ionization energy. So in this case, this term over here, the charge density, is a term that has a relation between nuclear charge and the atomic radius. Nuclear charge and atomic radius. Charge density by definition is the charge per unit volume. If we either increase the charge or decrease the volume, the charge density increases. The charge density is basically a measure of how compact the nuclear charge is within the atom. So the more the charge density, the greater will be the nuclear force of attraction experienced by the outermost electron, and the greater will be the ionization energy. Now, down the group. Down the group, it's the opposite. The radius increases and it the charge increases and the radius also increases. So now going down the group, the increase in radius has a greater effect. Has a greater basically the increase in radius affects the ionized change in charge density more. So going down the group, as the radius increases, the charge density it decreases because increase in charge does not have as significant effect as the radius. But we don't need to go into that detail. We just need to know the trends and slight explanations on that according to our syllabus. So basically, I'll tell you what you need to know. Charge density is the charge per unit volume. Charge density is charge upon volume. It shows how compact the nuclear charge is within the atom. So the greater the charge density, the greater the nuclear force experienced by the outer electron, and hence the greater will be the ionization energy. This is all that you need to know about the charge density. It is important to use the term charge density because I've seen it being used repeatedly in the marking schemes as an alternative valid point to the nuclear charge. So it's better to use both the terms to be on the safe side while writing an answer for at least 3 marks. Okay, so it's a keyword while answering questions, as most of the time radius is not constant and the nuclear charge does not change. Does change actually, it does change, sorry, it does change. So ionization energy actually it it is affected by both the nuclear charge and the radius. So whenever the ionization energy is affected by the nuclear charge and the radius, we are always gonna explain it in terms of both the nuclear charge and the charge density. Okay, so this is a lot about the factors affecting ionization energy. So to sum it up, basically, examiner's gonna ask you what are the explain the factors that affect ionization energy. So all that you need to know and write down in that answer is the 3 factors. First you need to first identify them and then explain them a bit, because a maximum of 3 marks question I have been asked so far. The 3 factors are the radius, the charge density, basically the charge density or the nuclear charge, and the shielding effect. and you need to write down what each one, the relation each one has with the ionization energy. Atomic radius, as it increases, ionization energy decreases. Shielding effect, as the shielding effect increases, ionization energy decreases. And atomic radius and the nuclear charge, as the nuclear charge increases, again the ionization energy, this time it increases. It doesn't decrease, it increases. Okay, so now let's move forward to a very important part of the syllabus. I've seen a lot of questions in the past year papers related to this topic, the trends of ionization energies across periods and groups. Okay, look at the blue arrows as I've drawn on this part of the periodic table. The blue arrow goes up and from left to right, ascending the group and across the period. Okay, ascending the group and across the period. In both the cases, the ionization energy, it increases. Okay, now these are two separate questions for 3 marks that have been asked in separate years, and each has been of 3 marks. So it's better to learn these points after understanding them. Okay, up the group, you know that up the group, yeah, you know that the period number of each represents the total number of shells in an element. So the first period, since it's one, so only one shell is present in both hydrogen and the helium in noble gases, which I haven't shown here. Then the second period has two shells, the third period has three, four, five, six, and seven. Up the group, the number of shells in each element, it decreases from 7 to 1. As the number of shells decrease, the atomic radius has to decrease. As the atomic radius decreases, the charge density, as I explained earlier, it increases because charge density is the mass per unit volume, and volume correlates with the radius. So as the volume decreases, due to the decrease in radius, the charge density increases. And these 3 points will earn you 3 marks. But to be on a safe side, you may also write shielding effect. Going up the group, the shielding effect decreases. So as a result, the outermost electron is going to be more tightly attracted to the nucleus, and more energy will be needed to remove it. So the ionization energy over here, the ionization energy, it increases. Now going from left to right, that is going across the period, the shielding effect remains constant because we know that the number of shells are constant. In lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine, there are two shells across this period. But the proton number from lithium to fluorine has increased. So the proton number increases, the nuclear charge therefore also increases because the proton number is responsible for the nuclear charge. The outermost electron will get more tightly attracted to the nucleus due to the increase in proton number and the shielding effect remaining constant. So as a result, the electron density around the nucleus, it will shrink, it would, and hence the radius, the atomic radius will decrease, which will increase the ionization energy because the outermost electron will get more tightly attracted to the nucleus and more energy will be needed to remove it. Again, 3 marks. So must learn these points because they are directly from the marking scheme actually. Now the last topic of today's video, finding group numbers from successive ionization energy data. This is a chart showing successive ionization energies of a few elements over here: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, etc. Okay, the first ionization energy, then the second, then the third, and then the fourth. If you observe something, the first ionization energy is less than the second ionization energy, and then the second ionization energy is less than the third ionization energy, and then the third ionization energy is less than the fourth ionization energy. Now, why is this so? Basically, I've given the explanation over here. When an electron is lost from an atom, the number of protons become greater than the number of electrons because obviously the electrons are lost, but the proton number remains constant. Therefore, the effective nuclear attraction, that is the nuclear attraction per electron experienced by the electrons, it increases, and hence greater energy is needed to remove the valence electrons, meaning the greater energy will be needed to remove the second electron as compared to the first electron which was lost, because this time the nuclear attraction has become even stronger. Therefore, more energy will be needed to remove it, and so the valence electron due to which uh, to remove the valence electron due to which the ionization energy will increase. Same goes for the third ionization energy because after the removal of the second electron, the third electron will be even more tightly attracted to the nucleus. So more energy will be needed to remove that. And same goes for the fourth ionization energy. Now the very last part of today's lecture, but let me remind you guys that this is a very important topic. This is a very important topic in general, and this part of this topic is also the most important because a lot of questions have been asked in the past year papers related to this one. Okay, how to judge the group number from this successive ionization energy data of an element? Over here, let's take the example of aluminum. First ionization energy is 577, second is 1820, third is 2740, but the fourth ionization energy has a very big jump. It's 11,600, a huge jump in between the third and the fourth ionization energies. This shows that the third electron, the third electron was the last in that quantum shell. Basically, the shell from which the first and the second electrons were lost. A third was also lost from that shell, but this fourth one was lost from the next shell, the inner shell, which and the fourth electron has a lower quantum number basically because it's from an inner shell, and its electrons are less shielded. Inner shell would mean that its shielding effect will also be lesser because the number of shells which are shielding this electron are lesser compared to those which are shielding the outermost electrons. So a very large jump in ionization energy is observed. It has 3 electrons in the valence shell, and therefore it belongs to group 3 because we know that the number of valence electrons is the same as the group number of that element. Group 3. 3 is in Romans, okay? Else in the uh, else it's 13. So this is how we are gonna find the successive ionization energy data can be used to find the group number of an element. Let's take another example of sodium. It's 494. The first ionization energy is 494, and then immediately it jumps off to 4560, and then it remains in thousands. But there is no such a big jump observed over there. The greatest jump, the greatest percentage increase is in between the first and the second ionization energy. Therefore, its group is the group 1. The first group is the group of sodium. Similar is the case with lithium. A biggest jump is observed over here, biggest percentage of jump uh, in the first from first to second. Okay, let's take an example of magnesium. Magnesium has the biggest jump from 2 to 3. It's immediately increased from 1400 to 7000, the greatest percentage increase. So it belongs to group 2. This is how we are going to use the successive ionization energy data to predict the group number of that element.